Yeah, let's get started. So we are going to talk about the first class support for Cassandra Materialized Views at Uber, CEP-48. My name is Ren Tian. I'm a software engineer working on Cassandra team at Uber. And
Hey, my name is Jaydeep. I'm also a part of the Cassandra team at Uber.
And my name is Xu Qi, and I'm also a part of Cassandra team at Uber.
so let's do a quick look at today's agenda. So we'll first talk about why materialized views are important, and then we will check the current problems with the old MV design. After that, we will introduce the CEP-48 with its MV repair spark job. And then we will deep dive into the key enhancements for the CEP-48 and as well as the MV repair job. In the end, we will wrap up with a Q&A session to answer any questions you have. Yeah, let's check why materialized views are important. So in Cassandra, data modeling is kind of driven by how you want to access your data. For example, for this school enrollment table, it's partitioned by student ID, so it's easy for you to query all the courses for one student. But if you have a new use case, you want to query by the course ID, like get all the students that enrolled in one course. If you only have this enrollment table, you will have to do a table scan. It's very expensive in Cassandra because the request may need to hit every node in the cluster. So this is a place materialized views can help. It will repartition the same data set with course ID. So you can query all the students in one course with this materialized view. So it provides better performance compared to the expensive table scan. So yeah, materialized view is a good feature, and it was introduced in Cassandra by 2016. But it was marked as an experimental feature because of all these problems. The first problem is the MV and base table get out of sync in the hot path. You know, we update the base table from time to time, and then you will see that base table and the MV get out of sync. One of the reasons for this is the lack of atomicity. The base table and MV are updated asynchronously. So when you finish updating the base table, you may not be able to see the update from the MV. And because of this reason, when you do base table repair, you need to replay, the current design will need to replay the MV mutations, which is a very expensive process because you need to, Cassandra will need to check the current state of the row and then generate the MV mutation and replay this mutation to the target MV replica. So this expensive operation has caused several incidents to us. So in our fork, we have to disable this path. The other thing for the current MV is the backfill process is not stable. When you create a new MV on existing base table, imagine you have a base table with billions of rows. The current backfill process is just replaying all the rows one by one. So basically, billions of messages flying around the Cassandra cluster. This process is very expensive, very CPU consuming, and it's not reliable. The last but not least is there's no way to detect inconsistency between base table and MV. And what is worse is that even if there's inconsistency and you somehow find it, there's no way to fix it. unless you drop the IMV and rebuild from the very beginning. But again, the current backfill process is not stable. So for production use case, first you cannot drop MV, and even if you are able to drop it, for large use case, it's hard to rebuild it. So yeah, now we're going to introduce the CEP-48 with the MV validation Spark job. So the goal for this is to get a materialized view from the experimental feature to a production-ready feature that by ensuring consistency and stability and observability. So for consistency part, there are two major things. The first thing is atomicity. Basically, we converted all the base table update to a LWT transaction. We wrap the base table and MV updates in one LWT transaction and backed by Paxos V2. So in this way, it guarantees the MV and the base table never get out of sync. So during the hot pass, unless there's some operational failure that caused some data loss, or there's some other bug caused data loss. So to make this consistency work in production, we also get this consistency validation job working, which is this MV validation Spark job. The second part about the stability, as I mentioned, because base table and MV are updated in one transaction, there's no way they can get out of sync. So repairing base table doesn't need to replace the mutations anymore. So repairing base table and MV replicas is just like normal repairing Cassandra. So and also the backfill improvements has also improved the stability. For observability, we added new metrics as well as toolings to monitor the status of MV and the backfill process. So yeah, can deep dive into each enhancement. For this strict consistency part, as you can see this diagram, on the left side is the happy path of the LWT. As I mentioned earlier, all the base table writes are converted to LWT write. The orange square is showing the extra hop we added in the LWT path to ensure that IMV and base table are updated in the same transaction. And as you can see, the unhappy path, if you get write timeout or write failure, the Paxos repair will make sure the IMV mutation will be applied in this transaction as well. So yeah, basically with this strict consistency, there's no way your MV and base table can get out of sync. After that is the backfill improvement. So as I mentioned before, the current MV backfill is replaying the base table to MV mutation row by row. And this new design works like this. For a given base table replica, it has some base table access tables. And this backfill command will first translate the base table data to the MV access table data locally without talking to any remote nodes. Once those access tables are built ready, they will be streamed to the right owners in the cluster. So this way, we translate all the messages into access tables and stream them away. So this backfill process drastically improves the efficiency of this backfill process of the materialized view. So For observability and configuration, we have added some metrics in the MV base table. As mentioned earlier, we converted all the base table update to LWT. This means if you want to migrate your current MV to use this strict MV, your write will become LWT writes. That means some writes is not which are not supported by LWT cannot be supported by this new design as well. For example, you cannot use timestamp when you write to base table. So the added metrics can help you identify if your base table can be qualified to migrate to this new design. The configuration for this is easy. We just do alter table to set this field to true to enable this. Feature. And then the third part is the added tools for MV backfill. You can initiate the backfill with the two, and also there's to check if the MV backfill has been successfully finished and if the MV is ready to serve read traffic. Yeah. So to summarize this change for CEP-48 is that it provides strong consistency and better stability with the price of the LWT. So if you have heavy workloads, it's good you can what you get out of the price is the strong, consistent guarantee that your base table and your MV will never get out of sync. However, if you want to run this in production, as I mentioned earlier, in the real world, sometimes data loss can happen and bugs are not avoided. So we need continuous validation job to make sure our materialized view and base table are in sync. So I will hand over to JD and Yuchi to talk about this MV validation Spark job.
Yeah, thanks, Rantian. So as Rantian mentioned, right now with the CEP-48, the hot path has become strongly consistent. So there is no way MV and base table can go out of sync, but there can be bugs and issues, right, or bit rot. So this is a luxury. This is one of the quotes from the discussion, community discussion, where one of the contributor mentioned that, yeah, good, like, you can make things in sync, but when you have two different tables, you need some peace of mind where like, okay, are they in sync or not? And that is one. And second, like if they go out of sync, what is the way to, fix them? And simply we cannot say that, okay, you drop MV and then recreate, because in production, it does not work at scale. So that's where this, Spark job is going to help the MV validation. So what it does at a high level is it uses Cassandra Spark connector. It connects to the Cassandra cluster. It dumps base table data. It dumps the MV table data. Everything in Spark. Then it uses the Spark sharding. So both the tables will be sharded based on the primary key of MV. So this avoids Spark shuffling, so that you can do kind of join and comparisons at scale without any performance penalty. And when you do full outer join, there'll be like 4 outcomes, as mentioned here, like, rows exactly match with the base and base table, which will majority be the case because now the online path has become consistent, but there can be like once in a blue moon scenario where, you could have bugs and issues. Then there can be inconsistency between base and MV table rows. Then rows can be present in MV but absent in base table, and the other way around. The job also has an option where you can optionally enable the configuration, and it will also fix those records. So here is the high-level architecture. One thing I wanted to highlight is the online path, the path that Rantian talked about, that has been officially accepted, in the community as part of CEP-48. However, this particular, Spark job is still up in the discussion. So it will continue to reside in the private repository until, we kind of do a formal discussion and an agreement over here. So at a high level, either an admin or cron job is going to trigger this particular job in step 1. Step 2, it uses the Cassandra connector, connects to the Cassandra cluster. It dumps the MV and base table, to the Spark based on the sharding mechanism I described earlier. And then it will do a different kind of comparison between these two data set. And in happy path, like there are no issues, so won't do anything. But if there are issues, it will either add, delete, or update MV records, and only point records. It will not touch the entire data set of MV. This is pretty much what I described. So the comparison is pretty memory efficient. So we only do Spark shuffling one time, because when we read from the Cassandra, it will always reshard based on the primary key of the MV. So both the data sets have exactly the same kind of keys. So they are on the same Spark partition. And it also provides kind of deep observability, where whenever the records do not match, it will stream exact differences between those records to kind of S3 bucket in different kind of files. And it will also generate aggregation statistics, where it will say how many records were consistent and so on and so on. And this has been kind of thoroughly validated at scale with billions of MV rows and tens of terabytes of kind of MV in production. Here is a concrete example, like in the first one you can see rows exactly match. So in the statistics you will see that, okay, let's say this many consistent record. In the second one there is a small difference between column 1 of base and MV, then it will mark this as particular record as inconsistent. If you supply that, okay, I want to fix this record, then it will also go to the Cassandra and fix this particular record for you. Of course, it will also output this particular record and delta, so you can debug it what happened exactly. And then the other two categories are like if a row is missing in MV and a found orphan in MV. In this particular job, it uses base table as the source of truth. It never ever updates anything in the base table. It only makes edits to the MV table. It has all the rich configuration. Basically, it uses all the open source kind of Spark configuration, where you can specify Cassandra kind of properties, including the throttling mechanisms, and this particular validation specific settings, like you can specify key space, base table, and MV that you want to kind of validate. And as I mentioned, it also has an option to fix records optionally. And but in case you have more inconsistencies, which will be unlikely with the new design, but there is a throttler and everything, so it won't bombard the Cassandra cluster. And yeah, I mean, it has deep observability, basically whether your job is running, whether it has failed, and how many records it is, comparing, how many inconsistencies it is fixing and found. So with that, currently the Spark validation job itself, generates the fixes and goes to the Cassandra cluster and says that, okay, fix this particular record. But there is a extremely corner case scenario which cannot be handled if Spark job does this this fixing. And as a result, we need to kind of take this particular comparison from Spark deep inside Cassandra. And my co-presenter Yuchi is going to talk about how we are going to do that.
Okay, thank you, JDip. So this is our version 1 design for how we fix this inconsistency from Spark job. So as JD mentioned, we figure out there are like 3 different kind of inconsistencies: missing in base table, missing in MV table, or we just like figure out some inconsistent records. So in this V1 design, we try to delete the records from MV if it's missing from base table, or we just rewrite the same records from the base table to the MV, or we try to insert the missing records into the MV again. There's some limitations here, obviously, because first of all, you cannot do like SQL writes towards MV by default. We made some change to allow it, but there's also some limitations like in SQL level, you cannot use this like using timestamp for different cells in the single statements. Because like when we are rebuilding this record, you want to use exactly what we read from the base table, timestamp, write timestamps or TTL, whatever. Because of this, when we have some MVs with like multiple columns, we will have to do these inserts and deletions like multiple times, and it cannot work at scale. The second limitation is that this native SQL write path cannot handle certain types of entries in the MV correctly. More details is in this ticket, Cassandra 11500. Basically, it's because of the liveness of a row in MV is semantically different from the base table. So it's not like you can treat it as like a purely table. It has some slightly differences. I'm not going to talk about that today, but all details is in the tickets. High level idea is that for the MV with like non-primary key column as a primary key, the liveness of that MV row is instead the column that is non-primary key instead. So because of these two limitations, we are trying to move this fixing responsibility into the Cassandra. So the previous Spark job would be just like a detection part and tells the Cassandra, no, okay, we have this primary key for this MV table, we want to rebuild it. So we will let Cassandra to actually decide how to fix it. So before it actually fix it, we try to do a read to the base table again. And from the read result, we will try to either generate the base table row again, or we decide to delete the row. And all of this, we will kind of consider the base table row and also honor the read time for example, if you want to read something from the base table, it's probably, there's nothing from the base table, you can return null. And for this kind of situation, we need to use the read time to ensure that we don't delete anything accidentally. Yeah, so this is high level idea of how this would work. It would just like be two actions. One would be rewrite or the other would be like delete. And all this would be done on the MVs only. Yeah, I think that's pretty much everything from this. We would be happy to take any questions.
Hi, thanks. This is maybe my unfamiliarity with Cassandra, but it's a basic question. Can you elaborate more on like how Cassandra keeps the MV replica in scale? Can you elaborate more on how Cassandra keeps the MV replica in sync, such that it doesn't contain stale data in case of like network partition or split brain something? On the last slide, I think.
Okay. How they keep inconsistent?
Yes, how the MV replicas are kept consistent.
Get consistent.
Yes.
So yeah, you can check the left side of this LWT path. So this is built on Paxos V2. Basically, Paxos, you need to do the prepare, propose, and commit, all those three process. And what this orange square added is that before committing the base table update, we need to make sure the MV mutation is applied. So in this way, we kind of wrapped MV update as well as base table update in one transaction. Yeah.
So basically, after prepare and propose are done on the base table, before you commit to the base table, you can do the MV update. So once prepare and propose are done in the Paxos, there's no way anybody else can update that particular record in the base table. There's no way. Yeah. Yeah, that's kind of a lock, you can say, Paxos provides, right? So once the propose has been done, that will be replayed no matter what. It provides a kind of no linearizability. So after propose is done, you have luxury to do whatever you want to do. And that's where before we commit to the base table, we replay, we apply updates to the MV table. And then basically it provides that kind of strong consistency guarantee.
Well, while I'm walking the mic over, I'm going to steal a question. Just like with your observability that you guys have for your Spark jobs, what type of numbers are you seeing with inconsistencies? Like how often, like at P99, are there errors that you have to fix?
So previously we used to see quite a lot because with the old design, there were no kind of consistency guarantees. With the new design, we recently rolled it out like few months ago in production. So far, no kind of inconsistencies have been detected, right? Because the online path has become strongly consistent. The only issue we would encounter is either bugs that we introduce in Paxos, like or some bit rot issue where the disk got corrupted and multiple disks have to be corrupted. So yeah, so far no kind of issues, but we will still continue to run this validation job because when you have two different tables, you need peace of mind that they are in sync or not.
For the validation job, we are using Spark-based. We are converting the base table to the MB, base table SS table to the MB SS table. Did we consider using repair? I mean, like we can convert the MB SS table to the base table and apply the same repair strategy. Did we consider and did you see any downsides to that?
Exactly. So that was one of the disks. So when we did CEP-48 in the open source side, that was one of the proposals to do not use Spark job. Basically use repair on MVSS table and base table SS tables. You can go through that discussion thread. It is one of the longest discussion threads came out to be. The unfortunate part is basically it looked like we are kind of re-implementing Spark inside Cassandra ultimately because these are two different sharding mechanisms. It's not that it is impossible to do it, but what we felt is let's kind of work step by step. So let's fix online path and do best of both. Like Spark provides you kind of guarantees. Spark provides you infrastructure to compare to different sharded databases or different tables. So as a community, at least for now in CEP-48, we proposed there are three things to be fixed here: online path, backfill, and validation. So in CEP-48, we reduced the scope to fix online path and backfill, which has been accepted. The repair was going on and on because, as you mentioned, right, there are many ways to be done inside Cassandra, but it was just becoming more and more complicated. So we said, let's park the validation part, currently keep it as part of the Spark, whose many people have Spark infrastructure, so they can use it. And after this has been kind of done, the patch and things are out currently, like, so once that lands in, we will resume the discussion around, the validation inside Cassandra. So that is TBD.
Yeah, actually, I think my question is similar as Sampri's question. So seems like the LWT will impact the latency, right? So have you considered using some asynchronous option to create the MVT or MV or repair the MV? For example, you can just replay the journal or replay the commit log.
Right. So currently, what to answer your question, we didn't deep dive. One of the ways is like CDC, as Bernardo mentioned, right? That is another way to kind of do it off async manner, right? But in Cassandra 6 also, many of you know that Accord is already coming, which will provide even kind of multi kind of transaction support across the shards. So given we wanted kind of, even with async path, there are like many kind of corner cases that we had to deal with, right? So we decided to go kind of strongly consistent as of now, and even if you look at the CEP-48 community discussion, eventually we want to converge on Accord because that anyway is going to provide a multi. It provides, like it's just matter of like when it's just matter of like time, right? So, and with Accord also, it will become strongly consistent. So as of now, until we have Accord, which might take like some time, we want people to have strongly consistent peace of mind, mechanism. And that is what, currently we thought about, going, because even current, the old design is async, and there have been so many corner cases and issues people had to deal with. So we just went with the, I mean, you have to pay some price, but then there is a peace of mind as well.
So for the Spark-based stuff, how does like a user run this? Do they have to have a separate Spark cluster, or I'm just curious, what's the operator experience for that?
Right. So people need to have a kind of Spark, kind of infrastructure, and then then the source code. We have the source code currently in the private repository, because it's, again, as I mentioned, requires a discussion there. But then admin can run it as well, like people can create cron job. So I mean,
Okay.
I
And do you have any like performance numbers for like when you went from async to synchronous using LWTs? Like what was the performance impact on that? It was good to hear that it went from like 99% to not almost fully 100%, but were there any latency impact or CPU usage increases?
So what we have done is we have used the Paxos V2, thanks to CEP-14, where it provides updates in 2 hops. Previously, it used to be 4 hops with the older Paxos version. Now with the Paxos V2, it can be done in 2 hops. With Cassandra, known for write performance, we haven't, I would say, seen a significant increase in the, it's not like 2x, 3x, 10x, because mostly Cassandra is very good at writes. And what we have introduced is, after propose is done, we just kind of, do writes, local quorum writes to kind of, to replicas. And that, again, within the same region. So, yeah, we haven't done a delta comparison between the old and new, because with the old architecture, CPU usage increases in general as well, not because it stores the entire updates in the system table, and the system table becomes bulky. And when you run Cassandra repeat like CP37, that also kind of puts a lot of pressure on Cassandra, and even it can kind of bombard your Cassandra nodes, and nodes could even go down. With this design, all those problems have been kind of resolved, with little bit penalty or some penalty you pay in the online path itself. So you get everything kind of for free.
It makes sense. Thanks.
Are there any performance numbers with Spark Validator? I mean, like in this case, we are using Spark Validator to completely scan the base table and the MB, right? Are there any benchmarking there? How much time it takes to scan a base table?
So we have run this on some sizable clusters. So there is one thing here is, currently it uses a CQL, Spark connector, where it uses CQL queries to scan the data. So, I mean, in terms of numbers, with, I would say, with tens of terabytes of data, again, you have to reserve some resources onto your Cassandra cluster, because it is not for free, right? It can be done in a day or less than a day. I mean, because the thing is, now this job has become a luxury as opposed to kind of mandatory thing. You can run, let's say, once a month or kind of once every 2 weeks or so, because online path itself has become rock solid. The next part of this Spark job is, as Bernardo and we have sidecar available, right? So you can, instead of using CQL queries to Cassandra and scanning the data, you just connect to the sidecar, and get the data from the sidecar. That way there is no Cassandra hot path involved. The only bottleneck as of today for this Spark job is we just don't want to bombard the live Cassandra cluster. Otherwise, everything else, once you have the data, then it is just a matter of like how many Spark resources you have. So I think our V2 will be like, use a sidecar as opposed to doing the SQL queries. And that way we can just run, it just becomes a factor of number of Spark resources because there's no hot path. So it can really go fast, like maybe a couple of hours for tens of terabytes of data. But yeah, I think that will be part two of this validation job.
Yeah, one thing to add here is that sidecar is is V2, because I believe a lot of organizations has backups. So we can do this validation targeting backup. So that's probably V3, and which will reduce the cost even. Yeah, I mean cost to the online Cassandra database. Yeah. So basically zero impact.
I think if you rely on like back SS tables, right, there is this one of having duplicates and setting up on quorum, right? Any kind of idea how we want to solve that?
I think that is already solved, right? The Cassandra analytics.
That's the analytics library.
Yeah,
Oh,
it's already solved.
Okay, they depend on that.
You need sidecar to work, but
And okay.